Hey everybody, Mr. Bowman here. Another 3.13 probability concepts video. This video we have a focus of the merit questions for the 2023 exam. Just a reminder, all of these questions are past NZQA paper questions. They're not my ones. I've kind of put them all together in one place for you. So check out the link in the description if you want to see all the other merit NZQA questions. So let's get straight into this exam. Question number 18 was the first one. And this one here, we've got two schools. We've got one in the North Island, one in the South Island. They've surveyed year 9, 11, 12, and 13 students and whether or not they like coffee or don't like coffee. So we can see that in the table. We've got the year level up here and whether or not they like coffee along the other axes. So 4 year 11 students are picked at random. Calculate the probability that at least one of these 4 students like coffee. So I guess the first step that I've done here is I've added on all the totals that relates to my table, because these two-way tables, they're good tools, but without totals you can sometimes get a bit confused. So let's add these together. So that plus that, so that means there are 56 year 9 students. Carrying along down the bottom, there are 49 year 11 students, and there were 52 year 13 students. We were told in the question there was a total of 157, and that worked out well because those three numbers did add to 157. And then going up the other way, we got 13 plus 11 plus the 22 over here. That was 46. So that's 46 people who liked coffee, and then the remaining 111 did not like coffee. So we've got our two-way table kind of done. We've got all the total. We now need to figure out this here. So I guess the big giveaway here is at least one. And if you've done probability distributions as well, it makes these things a bit easier. But if you're trying to find the probability that there is at least one of something happening, that's always equal to the probability minus, so 1 minus the probability of 0 of those things happening. So we now need to figure out, well, what's the probability that 0 of these year 11 students liked coffee? So that's what we're going to do here. So the probability that x was equal to 0. So how many people didn't like coffee? So we're looking at the year 11. So the people who didn't like coffee were 38 out of 49. So that's the first person. 38 out of 49. Okay, so we're now going to multiply that by the probability of the second person not doing or not liking coffee. So we now know there's only going to be 48 people left once the first person's picked. And of the 38 people who didn't like coffee, there's only 37 left. So that's going to be my numerator. So we've got 37. So we can see here that the denominator's dropped by, so the numerator's dropped by 1, right? And the denominator's dropped by 1. And now we need to repeat this for person number 3 and for person number 4. So person number 3, so that's going to be 36. Again, dropped by 1 because there's one less person who doesn't like coffee. Over 47. And then finally, hopefully you got the trick now. So we've got 35 out of 46. So I did that all onto my calculator. When I did that, I got 0.348, and that there was rounded to 3 decimal points. So I've now got that probability. I can now sum it in here to calculate the probability of there being at least one. So the probability of there being at least one is going to be equal to 1 minus 0.348, and that there is 0.652. And remember, that was impacted by our earlier 3dp rounding. So really nice question. And don't forget, this process works when you're dealing with at least one, because you can do 1 minus the probability of there being 0 happening. Okay, so we're now into question number 19, and this one here does carry on from the data that we had above. So it is believed that coffee is more popular as students age. Is this belief correct from the group of students? Use statistical reasoning for your answer. So what I'm going to do here is I'm going to try to calculate the probability within each year group that someone likes coffee, and then hopefully I'm seeing the year 13 one being the biggest number, the highest probability, and that kind of confirms that. If it doesn't confirm that, then that doesn't mean age. So it means age doesn't have a relationship. So let's find that. So I guess let's start off with the year 9. So firstly, what's the probability that they like coffee given they were year 9? So we've got our year 9, so it's going to be out of 56. So we've got out of 56, and of those 56, who liked coffee? And there's only 13 of them. So 13 out of 56, and because I'm trying to compare these numbers, I'm going to put it into decimal form, and I've got 0.232. I'm rounding to 3 dp here. I normally round to 4 dp here, but I'm going to do 3 for this one here. I'm now going to repeat the same for year 11, so I need to find the probability that they like coffee given they were year 11, and that's going to be out of the 49 year 11 students, only 11 of them like coffee. and that there is 0.224. So pretty similar, small drop actually, which maybe goes against what we've talked about. And then finally, let's repeat the same for the year 13's probability. They like coffee given they're year 13. Over there, don't forget, that's 22 people like coffee out of the 52. So 22 out of 52, and then that there is 0.423. We've done the math. I'm just going to type up the rest of my response here. So based on this, we can see the year 13 number is significantly higher than the year 9 and year 12, year 9 and year 11 number. So for me, I think that backs up the claim that coffee is more popular as the students age, and that's because the year 13s have a significantly bigger proportion of students who like coffee. So let's kind of write that up in a nice way. So year 13 students are much more likely to enjoy coffee when compared with their year 9 and year 11 counterparts. So that's me relaying the probability. I now want to specifically answer the question about the claim being made. This suggests that students are more likely to like coffee as they age. So we're now moving on to question number 20, and before I even read the question, just by looking at it, I know what type of question it is. Hopefully you do too. We can see that big list of bullet points. That's a dead giveaway. This is a three-way table question. And for a three-way table question, you've got to read the question, you've got to figure out what are the three variables. And here, you can kind of see them pretty clearly. One's cappuccino, one's flat white, and then the other there is mocha. So they're going to be the three variables we talk about. And you can see them also listed here, mocha, flat white, and cappuccino. So before I even read the question, I'm going to draw a three-way table for those variables. And I always draw these too small on the video, so I'll try to do a better job of drawing them bigger today. So this one here, so I always do them in order as they appear in the question. So mocha was first on the list. And then I'm going to add on my second variable here. And that there is flat white and not flat white. And then flat white, and then not flat white. And then finally, along the top there, we're going to do our third variable. Maybe I'll draw that a bit bigger, actually, because I need a bit more space in those areas. And that third variable is the cappuccino. So cappuccino and not cappuccino. So now that I've done that, I've just got to sketch out my the rest of my table, dropping that there. So remember, this needs to be into eighths. And we can see we've got the 8 there now. Amazing. So I now can do my subtotals. So I need a subtotal over here. That there's for the mochaccino people. That's the not mochaccino people. We've got the cappuccino people here and the not cappuccino people down here. And then down the bottom there, we'll have our grand total, which we actually were given in the question 510. So let's start by writing down that first number, 510. So give that a tick because I've entered that in. And I suppose I should note a relevant part of the question is, and this one's a bit different, the survey has allowed them to select up to 2 coffee types. So up to 2 coffee types. So that's a bit different. So what that means is they can't actually pick 3. So we can't have anyone who's picked M, F, and C. That there must be 0. So that's the first answer. And that one was really tricky. That was hidden. I only just spotted that then as well. So that there is 0, and that's kind of come from this up to 2 part here. We can have numbers everywhere else, right? Because that's 2 or less of the coffee choices. So we got 423 preferred at least one of these coffees. So 423 preferred at least one. And that's a bit tricky because if I shade it in the table, so that means all of these is at least one, that's at least one, and that's at least one. So we can't actually figure what out that means, but we can figure out what this number is from that. So if we go 510 minus the 423, that's going to tell us who preferred none. So 510 minus 243, that there is 87. So we've used that 423 to get to the 87. So we've now got 81 preferred cappuccino only. So cappuccino only is C, F dash, M dash. So we need to find that on the table. That's just a number we can put in. So we've got C is up here, F dash could be here or here, and then M dash is over here. So that means that's going to be this number over here, isn't it? So that there is going to be, what was it, 81. So I've got 81, tick. So we've now got the next one. 38 people preferred flat white only. So remember, flat white only, well, that's going to be F C dash M dash, isn't it? So F C dash, that one there, is that right? Hopefully it is. So that's 38. So we've now used that number there. 29 indicated that they prefer flat white and mocha. Remember, from this one here, they could only pick two only. So if they picked flat white and a mocha, that means they didn't pick cappuccino. So we've got FMC dash, that's going to be that number up there. So that's going to be 29. And then, so that was a tick. And then 103 preferred mocha only. So mocha only. So that means that was M F dash C dash. So let's find that M F dash C dash. So that's this 103 over here for the mocha. So I've used that number there. And before I get to the last bullet point, I can actually figure out this number here, can't I? So by adding up all of these, that's going to be 257, 257. I can figure out this number here. So 510 minus this is going to be 253. That's over here. And I don't think there's anything else I can figure out at this stage here. And then we've got none of the people in the survey indicated they preferred cappuccino and mocha. And this one here is a bit tricky. So obviously the number we're talking about here is 0, but it's referring to cappuccino and mocha people. And those are people who would have selected 2, which means the third pick, flat white, had to be not flat white to get 2 of the 3. So that means CMF dash. So CMF dash, this number up here, that's got to be 0. And that one there was a bit tricky to break down. I can now figure out this total up here now, which is 132. And then from that, I can figure out this total down here, 378. And then finally, up here, I can figure that out a few different ways, but the answer, I think, 172. It's 172, because that plus that must equal to that. And then all 4 of those must equal to that. Okay, so I've got my table done. I'm now going to figure out the actual question. Calculate the probability of, calculate the proportion of the people who indicated they preferred a cappuccino. So that there is probability of cappuccino. And this one's going to be really easy. It's going to be 253 out of the 510. So 253 out of 510. And when I put that into my calculator, I get 0.4, oh, forgot the bullet point there, 4961, is it? Yep. And that there is rounded to 4 decimal points. I just want to note this 3-way table question I thought was particularly easy. There's something I use called coding for these questions, and we didn't even need to use that here. So if you're wanting to tackle harder questions, check out some of the other videos. I think this is probably the easiest one I've seen. So don't expect it to be this easy in your exam. Okay, so we're now up to question number 21, and question number 21 was a pretty poorly done question. It comes from a different type of graph. Hopefully your teachers have looked at them in class with you, but do expect weird graphs to come up, and you've got to be able to break down the information to do it. So again, we've got 510 people were surveyed, so that maybe it's the same data as the last one here. This time around, they were checked if they were from a rural area or an urban area. We can kind of see that down here. And then finally, they were asked if they preferred to have coffee at home or to go to a cafe. We can see that by the colors. The graph, I'm not trying to pronounce it. I'm not an English teacher. My pronunciation would be very poor. Separates the two variables based on the rectangular region. So that's what we see here. But the issue is if you add up all of these here, all of those add up to more than 1. So that means this probability here. So this here relates to the probabilities for urban people only. And this here relates to the probability of rural people only. If we needed a probability of a total out of everybody, we would have to do some maths to do that. So reading the question down the bottom there, what evidence exists from the graph that there is a difference in people having a coffee at home or in the cafe between rural and urban areas? So the way I started this question was I did 4 quick calculations. So, well, they weren't really calculations in the end. So I found, well, what's the probability that they like to have coffee at home given they were rural? And looking at the graph, we can see all the rural people were here. And the home people, don't forget, that's in blue. So that's actually 0.825. I then repeated the same. Well, what's the probability they like to go to the cafe given they were rural? And again, by reading the graph, 0.1. 7.5, I can kind of see that proportion there. I then repeated these proportions for that, and it ended up me just stating all the numbers. So this is me breaking down the numbers. So probability that they were at home, given they were from an urban area, and that's that bottom number down there, right? 0.458, and then finally that top number there, that must be the people from the urban area who prefer going to the cafe. So probability of cafe given urban is equal to 0.515. Okay, so now that I've got that done, I'm going to do some relative risk calculations here. So I'm going to do my relative risk for my urban area first, or my rural area first, actually. So always big number divided by small number, so it's going to be 0.825 divided by 0.175. So that's that number divided by that top number there. When I do that calculation, I got 4.7. So 4.7, and that there had a 1 dp rounding. And then after that, we've got the relative risk for the urban areas, and I'll explain what both of these numbers mean. Again, big number divided by small number, so 0.151 over 0.485, and that's equal to 1.1, again with a 1 dp rounding. So because the numbers are the different way round, so here we've actually got home divided by cafe, and then down below we've got cafe divided by home. So what this 4.7 number tells us is people are 4.7 times more likely to prefer coffee at home than at a cafe if they're from a rural environment. And then the second one is basically the other way around. They're 1.1 times more likely to prefer coffee at a cafe than their home. Let's talk about those two numbers, 4.7 and 1.1, put them in a sentence. And then finally, I wanted to note, we didn't really read it at the beginning, but the question says support your answer with statistical reasoning with reference to sampling variation. So what we're going to do is we'll do that sampling variation bit at the end, but let's talk about the numbers first. So those who live rurally are 4.7 times more likely to enjoy coffee at home than the cafe. And then finally, we're going to do the same for the urban people. Remember, it's the other way around, at 1.1 times more likely to prefer it at the cafe than home. Whereas those who live urban are 1.1 times more likely to enjoy coffee at a cafe than at home. So that's what the numbers mean. So obviously that's pretty good evidence. So that's, good evidence that that they have different preferences, isn't it? So this is evidence that those living rurally have different preferences than those living, living urbanly. I'm not sure if that's the right word. Urbanly. There we go. Urbanly. Urbanely? I'm not sure if that's right. Living in urban areas. We'll do that. Okay, so we now need to talk about the sampling variation part. And remember, every time we take a different sample, because this here, it was quite a big sample of 510, so it does give us quite a good picture. But we must recognize every time you take a sample, your answers might be slightly different. But would those slight differences cause your impact to change? And we can see here, these are so different, these answers. So these group here overwhelmingly prefer coffee at home. These people here, subtly prefer coffee at a cafe, but the difference is absolutely huge. So I think there's no way sampling variability is going to cause this answer to change. So we're going to talk about that. So the differences in urban and rural people's coffee preferences are significant. They are unlikely to change if a different sample is taken, as there would only be a small sampling variation from our large sample of 510 people. So that wraps up this question here. Okay, we're now on to question number 22. Sorry if the audio has changed. I've just had to switch rooms to avoid some noise. But we've got question number 22. We've got 3 friends who are meeting up for coffee regularly. And then it goes on to say they've been analysing the strengths of the coffee, so they've got extra strong or not extra strong. and the brands. So the brands are either fair trade or not fair trade. So this kind of looks like a two-way table or a probability tree at the moment, right? Because there's two variables for each of them. Let's keep reading. 15 different brands were counted for, so 15, that number might be useful, and they've hidden that number in text as well, which is a bit tricky. 12 were from fair trade, so I'm pretty convinced now it's going to be a two-way table, because probability trees often will have, decimals and fractions and percentages as part of the answer, whereas we've got whole number integers, so that maybe tells me it's going to be that there. Explain if they're mutually exclusive. And perfect, because mutually exclusive is really easy to spot on a two-way table, right? So let's sketch out the table. If I'm wrong and it ends up being a tree, we can kind of pivot. But we've got that there. So there's my two-way table. It's a poorly drawn one, but so let's go with, we have extra strong coffee and not extra strong coffee. We've got the fair trade one and then the not fair trade one. And remember, we had 15 total. That was given to us there. They said 12 of them were from fair trade brands, so that's going to be 12 fair trade, 3 not fair trade. And then they had 8 were extra strong, so we had 8 extra strong here. We had 7 not extra strong here. And then it says of the 8, 5 of them were fair trade brands. So that 5 must go there, right? So that means that there is a 3, that there is a 0, and that there is a 7. So we've got all that discussion there, and we've been asked, are the events being not fair trade and not extra coffee mutually exclusive? So let's get into that. So basically, remember, so they're talking about F dash and E dash as part of their answer. So I always start with my statistical statements. So if F dash and E dash are mutually exclusive, then the probability of F dash and E dash must be equal to 0. And that's because if they're mutually exclusive, it means they cannot occur at the same time. So that means the probability must be 0. So let's go to our data. Let's calculate that from our data. So from our data, the probability that F dash and E dash, well, that there is going to be 0 out of 15, right? Because that works out well. So we've got E dash and F dash, 0 out of 15, which is equal to 0. And then now we can make a claim. So because the probability is equal to 0, it's matched exactly what we would expect from a mutually exclusive relationship. We can go ahead and confirm, lock in, that it's mutually exclusive. So this suggests, oh geez, I've missed the S there completely. So this suggests that the events, oh gosh, I keep missing the letter. The events of F dash and E dash may be mutually exclusive events. And you might hear the rain downpour in the background. I'm not sure if you will or not over the microphone. There we go. So we're now on to question number 23. Question number 23 was the final merit question for the 2023 exam. Let's smash it out. So we've got 3 friends are meeting for a coffee in a cafe once a week. They have a system for deciding who will pay for all 3 coffees, and that involves them flipping a coin. The friends who flip the coin different to the other 2 is considered the odd one out and ends up paying for all of the coffees. Explain with statistical reasoning why each friend can expect to pay the same number of times. So I just want to give you a bit of a discussion what this odd one means out. So let's say you flip the coins. Let's say someone gets heads, and then tails. So let's say that was the coins. So these 2 here have the same coin. This one here is different. That's the odd person out, which means whoever threw the tails is going to have to be the person paying for the coffees. I do want to note the question is silent. Let's say it was heads, heads, heads. The question was silent on that scenario, so it's probably going to have to be safe to assume that, if they all threw the same coin, they would just rethrow it until there was an odd person out. So the way I started with this question here was I listed out all the different options. So let's consider, so person number 1 can be here, person number 2 can be up there, person number 3 can get up there, and then over here I'm going to write, well, who actually ended up paying for that kind of round of coffees. So the first combination there was heads, 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 and that was in a scenario, again, we've had to assume it, they're probably just going to reflip the coin there. So from that scenario, we don't actually know who's paid. The next combination, just going to do them logically. We've got heads, heads, tails. That was the other one we did. So that means person number 3 ended up paying that one there, right? And then we've got, let's go heads, tails, tails. So just changing them up slightly. Person number 1 is the odd person out now. So they've ended up paying person number 1. So we've got heads, tails, heads. Hopefully I'm getting them all right. So that one there. So that's person number 2. So I'm expecting 4 heads initially, and then there should be 4 starting with tails now, because we know there's going to be 8 combinations in total, because it's 2 times 2 times 2. Let's do all the tails, tails, tails first. So again, we don't know who's paying there because they've got to reflip. We've got tails, heads, so that's going to be person 3 paying that. Then we've got maybe heads, heads. That's person 1 paying that one. And then finally we've got maybe heads, tails, I think is the last combination. Yep. And then that's person 2 paying that one there. So I've listed through all of my combinations here. And now I've just got to make sense of this. So we can kind of see, when people are paying, 2 of them are person 1, 2 of them is person 2, and 2 of them is person 3. So they've all got, from there, 2 out of 6 chance of ended up paying. And that's exactly what the question's getting at. So let's talk about maybe the probability of person 1 paying. That there is going to be equal to the probability of person 2 paying. And that there is going to be equal to the probability of person 3 paying. She's running out of room. And all of those are 2 out of 6 times. So we've now done that. We've now just got to explain what all this means in a short sentence. And really all I wrote here was, all the 3 people are equally likely to pay. So all 3 people were equally likely to pay for the coffee. Full stop. So that wraps up all the merit questions of the 2023 exam. I really do hope you find these videos useful. Now, just a reminder, these merit questions were all from NZQA. If you're looking for the other NZQA merit questions, check out the link in the description to this video, and there'll be a whole heap of them from like 2019 or something like that. And hopefully they really support and help your studies.